Hello everyone, today we'll be going over quantum cryptography. Quantum cryptography is a type of secret key encryption method where we'll have polarization states. So to make our secret key, we'll use these polarization states. These type of states are here on the right hand side where we have our diagonal pair. So when we talk about polarization states, we're talking about the polarization of light, such as photons. So if you've ever seen polarization glasses before, they'll look like sunglasses, and they block um, specific, not wavelengths, but a certain amount of light from getting into your eyes. That would be the photons. And if you've ever turned polarization or polarized glasses to the side, you'll notice that more light will go in or out of the glasses depending on the way or angle you hold them. That's because depending on the angle you hold glasses, it'll allow more or less, let's say, light to come in or out. Okay, or not come in or out, or how do I say, go through the actual material of the glasses because it's not fully transparent. So in this case, that's the type of technology we're using to make our secret code, or our secret keys, should I say. So we have a diagonal pair where whenever the light is diagonal, or I mean, whenever our polarization is diagonal, it will allow information through. If it's maybe going to this specific direction, it'll be our 1. If it's going in this specific direction, it's our 0. And when we're talking about making our keys, we usually use this. We'll usually use an X, that being diagonal. Okay, so it'll allow both zeros and ones through, so long as our polarization is the same on the other side. Okay, because as light comes through, right, you can almost think of it like this. If light comes through this way, it'll continue going through. Okay, but if light comes through this way, let's say, it's going to get blocked. So if we have maybe I don't know, a sender, okay, and a sender, you send maybe a vertical or horizontal pair, let's say photon wavelength that can go through. Okay, that would either be, let's just say it's this way, that will not go through our first polarization screen, you could say. Let's say we send a diagonal one through, okay, goes through, and then on the other side we have another diagonal pair, okay, it'll continue going through. But if we had a horizontal pair on the other side, okay, so we have a diagonal, goes through, okay, and then now we have that same wavelength trying to go through this vertical or horizontal pair polarization state. It won't go through, it'll get blocked. Okay, that's basically what's happening here when we're sending photons through our quantum channel, which we'll talk about just now. Okay, so that's what we're talking about when we're trying to make or let in certain bits to go through our, I'm just going to say, we call it our quantum channel. This would be our quantum channel. Okay, wavelength goes through. This would be the sender's polarization state, I'll call it. And this is the receiver's polarization state. So the receiver and sender will have their own states, and depending on which bits are let through, it'll make its own code that neither of them know about, but we will be able to use it as a form of a private key um, uh, that cannot be intercepted. Okay, so we'll go to the advantages and disadvantages of this. Well, as I said, it can't be intercepted, so therefore cannot be detected, so much better security. So it's basically impossible to hack. This is because, I mean, if you're sending a wavelength through your quantum channel and someone intercepts it, now they've got your key, right? But now they have to now replicate that exact, um, let's just say, code, yeah, the exact key, and send it through. They would have to make an exact replication of that. That's basically impossible since we don't even know what that key was originally. So they might be able to decrypt it, but they cannot re-encrypt it with the same information and send the same wavelength out. Or it can be possible, but it's basically impossible. We just say it's possible to hack. So disadvantages of this. So even though it's much better security, disadvantage is that we actually need a quantum channel in the first place. We can't just use normal wiring because we're sending light. Okay, we can't just use normal standard communication methods that we usually use. Okay, this is expensive, so it very high cost for this type of security method. So very few people actually need it unless security is paramount and the most important thing in your system. So now lastly, we'll just go over how does this work exactly. Let's just do an example. So when we create a secret code, or let's say secret key, so that can be secret code or key, right? That'll be in form of a bit, a few bits that we send. Okay, let's say we send a 10-bit line of information, correct? So if I had to send 0, um, 0, 1, okay, so it goes 0, 1, 0, 1, 1, 1, 0, 1, 0, 1. Send it through. This is our polarization that the sender has, okay? And on the other side, this is the polarization of the receiver. Whenever, so obviously you can see it can go through our diagonal, but it cannot go through our horizontal because the polarizations have to be the same. Or here it goes through our horizontal and vertical, and then it can continue going through, and therefore we have a bit that's received. That bit being the either 0 or 1 on the other side. Okay. Here, if polarization is not the same, no information. If polarization is the same information. So here polarization is not the same, therefore we receive nothing. Polarization is the same, we receive something. Okay. You can see these are all ones, but even with zeros, it's the same. These polarizations are the same, so we end up receiving our 0. Every time we don't have say polarization, no information is received, and that's essentially ignored. So the information or secret key that we get is 11100, and this is the secret key that was made up depending on the polarizations that you had. Okay. And since this is quantum, it's not really known by the receiver or the sender whether or not, like, what code or key did they get. It's almost random. It's not random, but it can be seen as almost random. So we don't really know what that key is. It's just an encryption method that we use. Now we have a key that we can use that cannot be hacked or cannot be um, stopped in between transmission so that you can hack or get into another person's information using that key. Once that key is intercepted during transmission, it's over. That key is done. Now a new key has to be made, and it's going to continue happening. So the hacker, basically, it's useless for them. they're going to continuously get keys that are no longer being used, because once it's been intercepted, a new key is going to be made. Okay. So that's the end of quantum cryptography. Hopefully you understood. Hopefully this wasn't too long, and thank you.